It is a very overwhelming, frightening, and exhilarating period for being away from home for the first time, but the most difficult transition for me was not having that built-in support group already on campus. I will say I was fortunate enough to be on the women's soccer team here, so that has helped me a lot having a built-in campus family. Also, I would definitely recommend finding organizations you're passionate about and just connecting with people that way. Ultimately, my end goal is to be a physician and do Doctors Without Borders. But first, I think it is very important to understand my community and what my community needs. So I plan on joining the Peace Corps after college. And what attracted me to my biology major ultimately was that I found it gave me the critical thinking skills to be able to challenge the world and to find ways to better myself and to better my community. And biology is ultimately the study of life, and life is ever changing, and that just really intrigues me. Hey guys, I'm Carol Johnson. I'm a biology major at Birmingham-Southern College, and I'm here to talk to you guys about enthalpy. Enthalpy is a thermodynamic quantity used to help determine the amount of free energy that can occur in a system. Enthalpy can be simply defined as the measure of energy gained or lost as heat from a system. Enthalpy can be understood as an endothermic or an exothermic reaction. Endothermic reactions are when the reactants absorb heat energy from their surroundings, so the reaction can be completed and products can be formed. Exothermic reactions, on the other hand, is a process where heat is released to form their products, and the temperature of their surroundings increase. Below you can see a visual of the two reactions. The ice is colder than its environment, so the heat is flowing into it, thus resulting in the ice melting. The other image illustrates how the fire is hotter than its environment, therefore heat flows out of the fire into its environment. The environment becomes warmer, whereas the fire becomes colder. Here's a graphical depiction of the two processes. The endothermic reaction graph displays that the reactants absorb heat so the products can be formed, whereas the exothermic reaction graph shows the reactants have more stored chemical energy and releases energy through the process of heat to produce products. The first equation listed is in relation to Gibbs free energy. Enthalpy is depicted with the variable delta H, or the change in H. Hess's law of formation is the following equation listed. Hess's law is the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants, meaning the amount of heat created in the products and reactants is the total amount of heat produced in the reaction. Hess's law also states that if a reaction can take place by more than one route and the initial and final conditions are the same, then the total enthalpy change is the same. When solving for enthalpy using Hess's law, it can be helpful to approach the problem with these simple steps. First, balance your equation and check the stoichiometry. Secondly, use the table of standard enthalpies formation to find the delta H for each substance in the equation. Remember, you can find this table in your book, most likely in the chapter or in the appendix. Also, it is important to be sure to check the physical state, like if it's liquid, gas, or solid, because they can sometimes have different enthalpy values, as well as substances that are considered the natural state of an element will have an enthalpy of 0 and may not show up on a table. The third step includes setting up your calculations. During this step, double check your stoichiometry and simplify your equation if you have the same substances on the reactant and product side. For the fifth step, plug and chug. Here you want to account for the change in sign on the reactant side. If you sum if the sum of the reactant enthalpy is negative, and then a negative times a negative becomes a positive. Finally, for the last step, ask yourself, does this make sense? For example, if the enthalpy comes out as negative, did you expect that, or did it seem too far-fetched? Okay, let's practice. Calculate the enthalpy for this reaction using Hess's Law and the table. If you want to, take a minute and try it on your own. First, we check to make sure the stoichiometry in the equation is balanced, which it already is, so we can move on to step 2. We use the chart from the previous slide to find the values for the heat of formation for each substance. Nitric oxide is 90.25 kilojoules per mole. Diatomic oxygen gas is 0 kilojoules per mole, and nitrogen dioxide is 33.18 kilojoules per mole. Now, for step 3. Recall the formula for Hess's Law, which is the sum of the products minus the sum of reactants. Note here that there is a number 2 in front of nitric oxide and nitrogen dioxide, so we multiply their heat of formation values by 2. For step 4, plug and chug. Plug in the heat of formation values for the substances and calculate the answer. Now, for step 5, we find the answer we calculated is negative 113.89. Now we ask, does this make sense? Which we would expect the heat of formation value for the reaction to be negative. So yes, it does make sense. Now for round 2 of practice. Let's try one more example. Calculate the enthalpy for this reaction using Hess's Law and the standard heats of formation given below. If you want to take a minute and try it on your own, please pause the video and go for it. Okay, how to solve this problem. First, we check to make sure that the stoichiometry in the equation is balanced, which it already is, so we can move on to step 2. Step 2, we use the values from the previous slide to find the values for the heat of formation for each substance. Ammonia is negative 46.2, nitric oxide is 90.4, diatomic oxygen gas is 0, and water is negative 241.8. Each are in kilojoules per mole. For step 3, let's recall the formula for Hess's Law, which is the sum of the products minus the sum of the reactants. Note here that there is a number 4 in front of ammonia and nitric oxide, a 6 in front of H2O, and a 5 in front of diatomic oxygen, so we multiply their heat of formation values by those different values. For step 4, plug in the heat of formation values for the substances and calculate the answer. Here, we calculated that the number is negative 904.2. Now we ask, does this make sense? Which we would expect the heat of formation value for the reaction to be negative and to be a large number. Okay guys, thank you so much for joining me as we learn more about enthalpy. I hope you have a great rest of your day.